Mike Harrison.
Hi folks. So as some of you know, my day job is designing sort of electronics for art installations, large scale stuff. That's the Heathrow thing that Mike was talking about. And I've done, one nice thing about doing this sort of work is my customers just want this thing to work. So you know, I can talk about the technical stuff. My customers don't care. All they care is it works. They're not bothered about IP or this sort of nonsense. So you know, I can talk about all the stuff and all the problem solving, which is what I'm going to do now. I've done work for quite a lot of companies in this field over the years. The first company I did work for is this company called Jason Bruce Studio. They're a London-based design studio, and they were like one of the fairly early people doing this sort of stuff, so adding interaction to architecture and this sort of stuff. And quite a few of my customers are people that have like used to work for them. They're not very good at holding on to staff, so a lot of people move off and start their own studios. So, and one of the things I've done over the years with them is things using large LCDs. So this is in London's Westfield Stratford shopping centre. This is basically, it's like a digital fountain. You get like these streaming effects of these LCD panels. And these are basically single pixel LCDs with a blue reflective background, so they catch the ambient light. This is another one. This is in the US more recently. These are using triangular LCDs, which are like clear. So the actual technology is exactly the same technology as an old LCD watches. It's like a segmented LCD with just one segment. Yeah, it's sometimes known as shutter glass, but it's bog standard LCD tech in sort of pretty much every way, just apart from the number of segments. So this is a typical panel. Say it's just a big piece of glass with the polarizers, and it can go either black or 50% transparent. That 50% is because you've got the two polarizers, so you're always losing half the light that goes through them. And for these sort of jobs, in the past, I'd done controllers like this, which are basically a massive load of I/O ports. So it's generally RS-485 data over multiples of these controllers. Each controller picks out a number of channels and it spits out the data to the LCDs. And the great thing about LCDs is they're super low power, maybe like 1 milliamp per LCD. So that installation, that Westfield Stratford thing, that entire installation is powered by 12 volts down one Cat5 cable. So that's one, like, yeah, LED installations, power is always a huge problem. The nice thing about this is power is just easy. The power side of it is super, super easy. So I think it was last year or year before, they wanted to look at using these in a slightly different configuration. This is for a wildlife information centre in Denmark. And what they had envisaged was like a three-dimensional cloud type setup. And the basic setup is we've got 3 projectors on a projection screen, and then the birds that are shown on the projection screen, I'll show you the video at the end. You've got birds flying around the projection screen, they fly off into the corner, and then they transition into these pixel LCDs. So some of that first section here, those are actually just translucent screens that the projection goes through, and then they transition into the LCDs. And we've got some photos of the final installation here, just to give you a sense of the overall scale. And so we've got this very transparent 3D cloud of LCDs. And the LCDs are all on these thin suspension wires. Each drop of suspension wire has around 5 LCDs on it. So we've got 2 wires. So we have power and data for those LCDs and a very sort of slim frame design. So some of the stuff I'm going to be talking about is quite technical, but there's also some like mechanical stuff. So hopefully there's something for everybody and some ideas that maybe you can use. So there's mechanical design, there's software aspects, and there's some of the electrical stuff involved. So the frame design, I came into this project slightly later than I would have liked, in that they pretty much had to order the LCDs and hadn't really finalised the frame design, how all the electronics and frame were going to work together. We talked before and I said, yeah, we can probably do the power over data stuff and like the PCB is going to be roughly this big. But when I came in, they had some like not particularly good designs for like just like an acrylic frame or something. Although I was, you know, in theory only there to do the electronics, I thought I could do a better job on the mechanics. I occasionally dabble in mechanical design, and when I do, it's almost always involves using PCB as structure. So, you know, the mechanical designers were looking at acrylic, 3D prints, whatever, and I was thinking PCB. But PCBs you tend to think as just like a flat, you know, rectangular object, sort of effectively a two-dimensional object. But that's not necessarily the case. When a manufacturer cuts a PCB out of a panel, they use basically like a routing cutter. So instead of cutting all the way through, they can only just, you know, if you ask them nicely, they'll only cut halfway through. So you can have a PCB which has slots, blind slots milled into the surface of it. You generally want to use thicker material, and you can do it with 1.6 mil, but by the time you take into all the tolerances and everything, you know, it's quite tight. So in this case, I tried a few different sizes, but 2.4 was about it was about the thinnest that we could get the sort of slot size we want. 2.3 and 3.2 are very common materials. Most PCB suppliers, and when I say PCB suppliers, I'm talking the sort you phone up and talk to locally rather than some obscure house in China that, you know, you get your $8 PCBs from. They will generally have like 2.4 and 3.2 on the shelf ready to go. They may even have 4.8. 4.8 is not as common, but it does exist. So this is the frame design that I came up with. So what you're looking at is these two PCBs at the side. If you imagine like a popsicle stick shaped PCB that you're looking at the edge of, it's got a slot cut in the surface, and the slot, the LCD sits in that slot. And then we have these two brass rods which are soldered into the PCB to lock the whole thing together. But they also actually provide electrical connections, which is on the next slide. And for the mountings, these are surface mount M2 threaded studs. These actually come from a Japanese company called Mac8, who do all sorts of really cool surface mount PCB hardware. Their website is terrible, but they do some really interesting mechanical stuff. The reason we have one stud on one side and two on the other is that they wanted to lock these LCDs at different angles, so they made a set of different brackets to translate from the vertical drop wire, which is always vertical because gravity, to then translate to produce the right angle. So that there were a number of different brackets they made for each of the different angles they derived from their 3D design. So electrically, as well as the mechanical support, these rods provide electrical connections. So the top one provides the connection from the second, one of the drop wires down to the circuitry down here, and the other one takes the other side of the LCD up to that side. So the LCD connections along the top and along the bottom, and that comes from the structure of the actual LCD glass. So this is what the LCD looks like. It's basically two sheets of glass, 1 millimeter thick, with all the LCD goop stuff in the middle, and you've basically got an overhang on each side, because obviously you've got an electrode each side of the LCD, doing whatever it does with all the chemical, electrical stuff that makes it go black and white. So this overhang provides a connection, and these connections are made with conductive epoxy. So they stick the epoxy in and glue this wire onto it. And so unfortunately, by the time we'd finalised the design, the LCDs had, because of the lead time, we had to have ordered them. So we got the LCDs with these wires. What we'd have liked to have done is actually get them without the wires, so we could then put them in the frames and then just put some conductive epoxy to conduct from that conductive clear coating straight to the PCB thing. But we'll do that next time. But it just meant it was an extra assembly step. So we had to solder the wires on. So okay, so we've got this 1 millimeter thing. We want to mill a slot out into the PCB to accept it. The problem is 1 millimeter is quite a small slot to cut into fiberglass. PCB fabs don't really like it. You quite often find that if you do like an online quote and they'll ask you what your minimum slot size is, and if you select less than typically 1.6, they tend to put a cost adder onto it. And if you want a lot of really long slots, they'll get really upset because they don't like breaking tools and they've got to run them really, really slowly. So what we ideally want to do is grip this 1 millimeter thick piece of glass in a slot that's much bigger than 1 millimeter without it flapping around. So here's how we do it. And this is actually a very useful technique for all sorts of, if you're thinking of weird things to do with PCB structure, you actually create this offset thing. So the thing you're gripping is rigid, so you don't have to clamp it in the same place. You can clamp it there and you can clamp it there. So that blue is the size of our 2mm cutter. So we cut this profile on it, so we get this sort of nice tight gap that holds our PCB where we want to hold it. But also because we had these epoxied wires, we had all this fairly random rough goop on the top. And obviously we didn't want to have to deal with that when we clamped it, so we're clamping the top right at the edges. We still had to use the knife to cut a few bits where they put a bit too much epoxy on, but it means that most of that area is clear. We can easily just grip the LCD, and we're using just standard router tool size. So that works nicely. But this technique is really handy if you want to, say, have PCBs that slot together for actually for doing this. It's quite a useful technique. So this is what the PCB ends up looking like. So we see this routed slot shape. There's the silver pad, that's where the LCD wire solders onto. And these are just the two sides. You've got one side with just these two surface mount studs. And so these studs, they come on like tape and reel, so you can feed it into any pick and place machine. Although there were some minor issues with this. Because the top side of those studs isn't completely flat, you could only get quite a small nozzle onto the top of it, because where they press the threads onto it, you got the end of the stud, and it sort of bows up a little bit. So that the nozzle that you can get is quite small, and it turns out that nozzle is so small it can't actually carry the weight of the machine, of the metal part. So we actually, on my machine, I actually had to use a much bigger nozzle that grips it around the base, and the whole threaded part actually goes up into the nozzle. But we worked around that. But if I was dealing with a third-party subcontractor, there might have been some interesting conversations around that. But that all worked out quite nicely. And so we've got the control electronics on here. That's the PCB layouts. You'll notice this big red rectangle. That does serve a purpose, which I'll go to right at the end. That's a very subtle thing, which is quite an interesting aspect of it. And also, 2.4mm thick boards. If you do a traditional routed panel with normal breakout pads, it's really difficult to break 2.4mm PCB. So because we were doing the depth routing anyway, we just used that to thin out the routing tabs. And because we wanted nice smooth edges, I actually, instead of snapping these out, I used my cheap 3040 Chinese engraver to actually cut these out of the panels after the machines they were assembled. So we got reasonably clean edges on the boards after assembly. One issue though is we wanted these things to be nice and black. And okay, surface dead easy, matte black solders, it's no problem. But of course we want the edges to be black as well. And I did make some inquiries because, of course, fiberglass, it's just like it's a resin and a glass layout, so it starts off a liquid. So, they could put dye into that liquid to make up coloured FR4. And this stuff does exist, but there was quite a big, lead time and also a minimum order size. We were making, I think maybe 10 or 12 panels like that size, so, it would have had to buy a ridiculous quantity. So we had to think of another answer of how to put the black colour on the edge of these PCBs. That instantly we made, there I think are about 300 nodes, so 600 of these PCBs. So how do we put this colouring easily? Somebody, not me, did sit there going, it's quite quick once you get the hang of it, it works quite quickly. We bought one of every type of marker we could find just to find the best colour match, because a lot of these are actually more purple, but that worked really nicely, and it's nice and black. So that's the mechanics. That's all quite neat. I don't have any details of the brackets. I wasn't totally happy with the brackets they came up. I did actually come up with a bracket design using PCB, but it didn't have quite the right number of possible rotations they needed. So I'd let them get on with it and said, okay, it's your problem, guys. Deal with it. I've done my part producing the frame. So electronics. Let's take the glass. LCD is basically acts electric like a capacitor. When you put a voltage across it, all the LCD molecules twist, they change the polarization, and you get the LCD effect. But you have to drive them with AC. They will work with DC, but long term, you get electrolytic effects that deteriorate the electrode, so you must drive them with AC. So the obvious sort of thing, okay, AC, so it goes positive and negative, that's the obvious approach. You hold one at ground, wiggle one positive and negative, which you can do and works, but generating that negative drive, it's more complicated. Fortunately, the LCD is isolated. The LCD doesn't know where ground is, so if you actually drive it with these waveforms below, as far as the LCD is concerned, it's exactly the same thing. So if you just take those two waveforms, you subtract them, because the LCD is only looking at the difference, you get exactly the waveform you want. So now we can simply drive these with two 5-volt logic levels, so we can just use standard microcontroller outputs to drive them. And as you saw, those first multi-channel controller boards, they were just using standard 74HC595 in pairs just to generate all the waveforms. So that's simple. It reduces our drive task. And the current is very low. They are quite capacitive, so you generally want to add some series resistors to avoid a current spike when they switch. But other than that, you can drive them quite happily with standard logic. Unfortunately, 5 volts is usually about the sweet spot of these things. They rarely need any more than that. So they sometimes can deal with less. So that's all good and nice. The other thing we want to do, we don't want to just turn these on and off, we want grayscaling. Of course we want grayscaling, so it's got to look nice. So grayscaling is actually quite easy. You can do it by changing the voltage. The problem is that the transparency versus voltage curve is non-linear, it's temperature dependent, and it varies from LCD to LCD. So you don't really want to do that. So it turns out that almost counterintuitively, PWM works just fine. You get very consistent performance. So you drive at the top, that's our 100%, so that'll be fully black, and then 50%, they're only on VAR for the time. And because it's capacitive, it tends to smooth itself out, and it works nicely. You get some quite nice grayscales. The problem is that we want to use the PWM peripheral on a microcontroller, and multi-channel PWMs tend to want to start a pulse in one place and have different lengths of pulse from the same place, which is not quite what we want. But fortunately, we can bend ourselves around that quite easily. We have our two PWM channels creating variable width pulse from the same starting point. But we can also say, okay, but we want to invert one of those. And it turns out that when you do that and you apply the appropriate arithmetic to the values you put in, you can get exactly what you want very easily. There's one special case in the case of 0, but you could just add a fudge factor, just turn both outputs off when you want them to go to 0. So the PIC we used, it was a 10F322, which is a little 6-pin SOC23 PIC, has two PWM peripherals, so it was a perfect fit. So that worked out super easily. Now, the other thing we wanted to do is data over power, or power over data. So we want these two suspension wires, say, I think I designed it to handle up to 10. In practice, I think we ended up with about 5, because again, I was doing this design while they were still working on the final 3D modeling, so they didn't know quite how many LCDs they wanted on each drop, but they knew it was never going to be more than 10. So we have these two wires, we want to provide power, but we want to be able to select any LCD to any grayscale, so we need data and power over those two. And data over power is not uncommon. There's quite a few applications where you see it. Satellite TV antennas, they stick DC up the coax. GPS active antennas do the same thing. Power over Ethernet, they're all combining usually fairly high frequency data with DC power, and quite often it's just a simple case of putting an inductor to split the two, because the frequency is so high that a small inductor will do fine. So that's not quite what we want, because our data rate's going to be much lower. We've got like 5 or 10 LCDs. We're updating at maybe 30 frames a second. We're sending 1 byte to each LCD, so it's not much. There's some other considerations. We've got these two suspension wires, and the LCDs might have to go on either way, so it has to be polarity agnostic. We've got quite long suspension wires. I think the ceiling height was something like 4 meters on here. So we've got all these big 4-meter vertical cables which make nice big antennas, so they're going to pick stuff up, they're going to radiate stuff. If we put like high frequency in it, it's going to be a total mess. There was stainless steel. Copper is not a very good structural material. Stainless steel is much better, but stainless steel is really resistive. I think it was of the order of maybe 10 to 12 ohms for these drop wires. But fortunately, the LCDs, the node with the electronics, it was, I think, 1 to 2 milliamps, depending on whether it's black or white. So that's not an issue. Voltage drop we just don't really care about. I say we've got a very low data rate, so that's easy. Lower is always easier. But also the actual power draw from the LCD node wasn't like pulsing too much. We're just, we're clocking this LCD at, I think, about 250 hertz. That was all pretty much because that was about the lowest frequency I could get the PWM hardware to work at. It's very non-critical. You can, I think, anything from about 1 kilohertz to 50 hertz. You can't see any visible difference at all. So there's just a little bit of capacitance on the node, so that what you're seeing effectively is DC, there's no noise on there. Previously I've looked at doing the sort of thing with LEDs, and it's much harder because you've got much higher currents to deal with. So you've got the current draw from what you're driving is potentially interfering with your data. So that can be really nasty. I've never looked into that far enough to know how I know enough to know it's difficult, and I try to avoid it if possible. So we power the nodes with AC. We're running at 9 volts, and we regulate that on board to 5, so we don't care about voltage drop. We can have like 2 volts of voltage drop. We just don't care. And again, when I was designing this, I didn't know what size the suspension wires were going to be. I didn't know how long they were going to be, so let's allow for a worst case. And we then encode our data into that AC waveform. And the code chosen was a Manchester-type coding. There's a few reasons for this. Firstly, the actual data is purely in the transitions. The polarity doesn't matter. It's the timing between the transitions. So it doesn't matter if it's a low to high or a high to low. That's what gives us our data. One slight concern is we had ceramic capacitors on here because ceramics are smaller, cheaper, etc. And sometimes if you put an AC signal across a ceramic capacitor, you get some audio because they're piezoelectric. You may have seen, if you've ever played around with ceramics in like switch mode switching regulators, you may have actually heard like a little buzzing or a singing from them. And obviously we really didn't want that to happen. So the other issue was that because we've got these, although we're not putting much current through these things, there is quite a lot. And again, I was being ultra paranoid. I thought, well, okay, maybe if someone has one of these induction loop hearing aids, perhaps there might be a little bit of breakthrough. So I decided that I want to keep all the data components above audible, so above 20 kilohertz. So even if the capacitors sing, if it couples into a hearing aid, you're not going to hear it. So that's how I determine the data rate. So it's 50 kilohertz. And so the nice thing about the Manchester code, you've basically got 2 frequencies. So you've basically got 20 kilohertz and 40 kilohertz and no lower frequency components. So yeah, that did the job quite nicely. And the Manchester code, it's slow enough. That was just all decoded in software. It just generates an edge interrupt, and it decodes it all in software, because all the processor is doing is waiting for this data and then just spitting it out to the PWM peripheral so it can sit there. It doesn't matter if 90% of the CPU is decoding this data. As long as it always decodes it, that's fine. So this is the what's in the LCD node. We've got a bridge rectifier at the front end to get us our DC. We've got a couple of current limiting resistors so that when we switch, we don't get the current spikes because of these 10 microfarad capacitors. We've got this 47K resistor because obviously we need to look at the data, so that's going into the PIC. And as far as the PIC's concerned, that is going to be swinging up to plus 9 volts and down to minus 9 volts. So that 47K resistor, in conjunction with the input protection diodes on the PIC, means that clamps it to the PIC's 0 to 5 volt voltage range. And yeah, so we've got 2 resistors on the output drive to the LCD. We've used 2 resistors so we get a symmetrical drive. And because of the capacitance of the LCD, those resistors mostly avoid getting current. Yeah, they limit the current surge. So it's limiting the radiation from the cables. It's also limiting the power spike from the PIC supply rails when it switches, so it doesn't brown out or doing anything. This pad on the right, this was this big pad that you saw on the PCB layout, which I'll talk about in a minute, about why that's there. So very simple. One nice thing about this PIC is Microchip will supply them ready programmed from the factory. For these PICs, I think there was something like about 40 cents for the PIC and about 4 or 5 cents for them to program it. So we're putting ready programmed chips on the board. So it makes life a lot easier. Even if that only has the bootloader, it makes life easier. Obviously, these things, the PICs can do self-programming, so we can update the firmware over this 2-wire data link as well if we need to. The driver that was driving these is very simple. I'm using a Mosfet driver, which is basically just a moderately high current driver. It drives high and drives low in a reasonably high density package. They're fairly cheap. We've got these 22 ohm resistors which control the how fast that data swings on the line, again, to reduce the noise. We've got this common mode filter. That's primarily so that if someone's using a mobile phone next to it, hopefully that's not going to get back and do all sorts of nasties to us. It's going to hopefully chop that all out. And we've got these fairly big 10 nanofarad capacitors to just keep everything as slow. You know, we can get just about enough slew rate that we need and no more, because anything more is just going to be noise. This is running from 9 volt supply. The nice thing about these Mosfet drivers is they've got quite a wide supply range, up to like about 12 volts. So they're quite a nice way of producing a moderate current. I think they're rated up to about 1 amp or so. but at a higher than like 5-volt logic level, so they're quite handy for that. The other thing here is that there's a current sense, and again, I'll talk about that in a sec, because that's a quite subtle feature that actually turned out to be really useful. So this is the overall structure and arrangement. We have these channels in the ceiling. At the end of each channel, we have this power and data splitter, which is on the next slide. We have the vertical drops for each LCD. And then we have a power and data cable linking these. So we've got 24-volt power, RS485 data. Each of these splitters has its own device ID. And then the LCD we have an ID within the drop. And each drop has its own ID, so we can address any LCD there's a packet comes across the RS485 that's got a packet of data for each LCD, for each drop. And this is the power and data splitter. That PIC is actually the same PIC that's on the badges. We've got the Mosfet drivers on the right-hand side, RS485 receiver bottom right. This chip at the bottom, this is an analog multiplexer. This is taking that current sense that we saw, that's basically multiplexing the current sense input from each of these stages. And again, I'll go on to why we want to sense the current on those. It's not to do with fault protection. And there's a switch mode regulator to take our 24-volt incoming supply down to the 9 volts for the LCDs and also the 3.3 volts of the PIC. So that's all pretty straightforward. There's an RGB LED there, which via a light guide actually poked out the end of the channel. So if you looked at the side of the channel, you could see this LED, so you could tell that it's got power, you could tell that it's got data. So if this thing is just suddenly not working, you can immediately look up and see, is it a power problem, is it a data problem, which is a really useful thing to know. So we've got all these LCDs, we want to address each one individually. How do we do that? So what we really want is an ID associated with each of these nodes, these little PCB modules. And there's a few ways we could do that. I mean, for bigger stuff, I just stick a dip switch on it. Obviously, that's not really practical size-wise. We could maybe have some solder blob links, so you hard ID each one. There's only like 5 or 10 IDs, we could do that. We could pre-program it. We could take our thing, we could stick it in some sort of jig and program it, so this is ID 1, this is ID 2, then we hang them all up. The problem with that is it's a bit of a pain. It means that you've got to keep track of which one's which, you've got to label them all, but in particular, if you then got to replace one like 3 years down the line, you've either got to keep stock of each ID or you've got to have some way of programming those IDs into the stock. So it's a bit messy. And this is a problem I occur on lots of different installations. So this is sort of a subject which I've dealt with a lot. There's a lot of applications for it, and it can solve a lot of problems. So we take the general situation. You have a bunch of things on a common bus. That common bus could be radio. It isn't necessarily a physical wire bus, but where you've got a bunch of stuff all listening to the same data. And you want to say, this thing is number 1, this thing is number 2, and you often want to associate that ID with a physical position. So it might be a big array of LEDs, it might be an array of sensors, or a pile of LCDs. And there's a really nice way you can do that. You have some way of locally sensing a manual action at that node, and you just send a command down your common bus that says, if you can see that action happening, this is your device ID. So let's say, for example, it's a button, you set the control system, it says, okay, ID 1, press the button, ID 1, ID 2, press the button, so on, so that your device takes that command, finds the ID, sees the button pressed, and it's almost like a chip select. It says, okay, that's my ID, it then maybe writes it into its own internal non-volatile memory, so that's that device then programmed. So yeah, this makes the whole procedure. So for example, you hang all the LCDs and literally you go from LCD to LCD. You know they're in the right physical position. You just go through each one and all your IDs are done. If you have to replace one, again, you can repeat that procedure and do the same thing. Now, this switch could be almost anything. And a lot of the time, if your device already has some sort of input, you can just use that. So it's always nice to be able to not have to add hardware just for this process. So a physical button. It could be you short some, if you've got like a little thing, maybe you can just short some pads with a link or some tweezers. Capacitive touch is nice because it costs nothing. You just have a pad on your PCB, you stick your finger on it, and that gives you your input to say, yes, it's you. Magnet sensor, if your things are potted or an enclosure, you can't get to it, magnet. Do it that way. Hall sensors are like 30 cents. So that works nicely. Light sensor, maybe these things are up on the wall. Maybe you could do it, you shine like a flashlight across each one to tell it, I want this one. There's all sorts of ways of doing it. Accelerometer, I've done one installation where you literally physically tap each one because it had an accelerometer in there already. So you go around, tap each one. So almost anything. And literally every one of those I've used at some point in some installation. Every one. But as you can see, this is clearly something that's, there's all sorts of uses for this. So for this application, one thing is these things are all up, hung on the ceiling, they're hard to access. So it's conceivable that maybe someone's ID'd them wrongly and we need to change an ID with something on the end of a long stick because we don't have to go in with the cherry picker and the ladder and actually get to it. Again, it's one of the things, it may not happen, but if it does, it's a real pain. So if you can design that, so there is a way to do it, it's going to make everyone's life easy. So we look at all these options. So we take these options, but we might want to do it on the end of a long stick. We also don't want to add any component cost. I think there's some formatting disappeared. I was starting to cross some of these out because of these requirements. But I think in the converting to XLS, it's lost those. But basically, we come down to capacitive touch. It was about the only ones that don't add cost that are potentially doable from a distance. So in theory, yes, we could have a touchpad and we can maybe have like a conductive foam on a long stick and do that. The problem is that this side is quite close to the wire. It's difficult to get at, and for a touch read on a micro that doesn't have dedicated hardware, you need quite a hard touch. You're looking at basically how quickly a pin pulls up. So what you really want is a proximity. You want it to detect somebody is like fairly close, but not quite touching it. But proximity sensing is difficult. But so instead of capacitive touch, capacitive something else. Maybe we detect a signal from some sort of external device. So we're on a fairly high frequency, so that, we're talking about very low capacitance, so it needs to be high frequency to get enough signal across. So tens of kilohertz just feels instinctively about right. It's not really that critical. We want a moderate voltage again, so that it doesn't. We're going to make one or two of these things. It doesn't matter what it costs really. So plenty of voltage, so it'll work from a reasonable distance. We've only got this tiny little PCB strip as our antenna. Obviously insulated because we don't really want to put 100 volts on our electronics because that would be bad. It would be nice if we can have off the shelf because we don't want to have to get more things, but that didn't quite work out. This almost worked. This is one of these little fluorescent tube counterfeit money checkers, and if you just stick a bit of wire on the output of that actually almost worked. The problem was you want a button, so you want to hold it near the thing, then press the button when you want it, and there are a few other issues that it didn't quite work, but almost. But the idea of like a cold cathode fluorescent lamp inverter was pretty much close to it. So I just literally got one of these off-the-shelf inverters, stuck it in a box with a button and a double A cell. These I think they're meant to run on 12 volts. I ran it on 1.5 volts, so it produced enough voltage, and that worked. It's just a wire loop, so you could just get that loop onto the side between the thing and the suspension wire if you needed it. So that worked, that did the job. Now the reason for that current sensing, if I go back to this one, if you look at the stretch goal, in the process of doing these IDs, if whatever is sending the hello, you're going to be ID 1, can detect when you've pressed that button, that can then say, okay, that one's done, now ID 2. So literally your process is literally you go 1, 2, 3, done. So what that current sensing was about was that once that ID has been assigned, the LCD module can then increase its current consumption as an acknowledgement so that the controller can sense that's happened and automatically increment it. Now, how do you make this thing increment its current consumption? Remember, you're driving this capacitive LCD. So if you suddenly go from your, say, 250 hertz PWM to maybe 2 kilohertz, you're going to increase your power consumption. So to that acknowledge it, all I do is I simply increase the PWM frequency, which maybe makes it go from perhaps 2 milliamps to 4 milliamps, and that current sensing on the driver can detect that, so it can move on to the next ID. And in fact, that controller board can actually do it completely standalone. If you put the dip switches in a certain position, you'll see a red LED, you ID 1, it will change to green, blue, whatever, so that's completely standalone. That's it. I've just got a short video showing the final system in motion, which is there, I think. That one. full screen. How do I get the full screen? Is that right? Yeah, can you get that full screen? Projected onto. And one. And if you want to see them, there is actually a sample of 4 LCDs just as you come in. The wall that you see when you come in the door, there's a little hanging string of 4, so you can actually take a close look and see what it looks like. Okay, we've got time for questions. Or ask me later if you've got any questions.